Situational awareness is everything in the heat of combat, and this helmet does everything it can to keep the pilot informed, even giving them X-ray vision and night vision.
Alright y'all, welcome back to Commodore Arms channel. Okay, today we're checking out a video from the Real Engineering YouTube channel. Now, we've checked out their video previously about the insane engineering of the Javelin, and that was really cool because like the graphics were fantastic, and it went like super in-depth as to like the physics and everything going on, the engineering, I guess. But this one is all about the insane engineering of the F35B. I'm not sure if you say F35B or F35 Bravo, so maybe some like the Air Wing people are cringing at that. But yeah, I know the F35B is like the Marine Corps' variant of the F35, the vertical lift variant. The F35 Alpha or A is the Air Force equivalent or variant. And then the F-35 Charlie is the U.S. Navy variant. So I'm not exactly too sure on all the differences, but this one, again, it is like the vertical lift variant, which is pretty freaking cool. And I'm sure this video is going to go pretty in-depth, so let's check it out.
I've never flown an aeroplane like this, where you can control the motion of the aeroplane so precisely.
Huh. It looks like so cool.
Scratched the surface yet of what this airplane, when it's operating with other F-35s, is going to be able to do.
What did he say?
What precisely?
I'm not sure we've even scratched the surface yet of what this airplane.
Am I the one hearing surface shit? I don't know if he was like trying to work that in, or maybe I'm just hearing it wrong or something. I do have like a little bit of like a cold, but
I'm not sure we've even scratched the surface yet of what this airplane, when it's operating
surface
with other
yet,
F-35s,
I
is going
think.
to be able to do.
Okay.
The F-35B is arguably the most advanced plane ever made. A jack of all trades,
So
a
cool.
stealth fighter plane, combining and improving on the capabilities of the F-16, AV-8B Harrier, and the B-2. A highly maneuverable fighter plane.
I don't know like where they got this footage from or if they made it themselves, which I wouldn't be surprised, but it looks like so cool.
Capable of attacking both airborne and ground-based targets. A stealth fighter taking the lessons learned from Lockheed's previous ventures into stealth with the F-22 Raptor and the F-117 Nighthawk.
Sick.
A plane
That
fitted
thing
with
looks
the most
so odd
advanced
now.
sensors and computer systems, sharing information almost instantly with allies without compromising stealth, and presenting the information directly on a heads-up display on the pilot's helmet visor.
Dude, I really wonder how much those helmets are. Like, they've got to be like $200,000 just for the helmet.
Bruh.
I mean, look at it. It looks like it's all carbon fiber and stuff as well.
Giving
Jeez.
unparalleled situational awareness, allowing a flight of F-35s to effectively fight as a hive mind. Perhaps most boldly of all, the F-35B is capable of transitioning from horizontal to vertical flight with a push of a button, using directional thrust and
It's
a
so
massive
trippy.
vertical turbofan engine hidden within the plane's body, making it possible to land like a helicopter on the relatively small
Dude.
amphibious assault ships of the US Marines.
It looks like a freaking glitch. Like if you accidentally spawn a vehicle in a video game and it like either starts like clipping into the air or starts coming down. That's what it looks like. It looks so trippy. Like vertical lift, like aircraft are just so like odd to me. Like it's just insane engineering.
This is the insane engineering of the F-35B.
Dude, those animations are so sick.
Fitting all these capabilities into a single airframe is an extremely difficult task. Designing for stealth demands careful molding of the exterior of the plane, dictating the design of crucial features, creating unavoidable
slick.
trade-offs. There are a lot of misconceptions about stealth. The goal isn't to make the aircraft invisible. It will be detectable. The goal is to delay enemy detection for as long as possible. For bomber
Okay.
aircraft, it
Makes
shrinks
sense.
the range of the enemy's radar stations, potentially opening gaps in radar defenses and allowing the aircraft to slip through undetected.
Okay.
For fighter aircraft, it provides a critical advantage. Detect your enemy before they detect you. To gain these advantages, we need to make it harder for the radar receiver to decipher whether the return signal is just background noise or an enemy aircraft.
Oh my gosh, that's so freaking cool. Is it refueling right now? Dude, like, I don't know, anything that the F-35 does just looks so cool because there's like so many hidden compartments and whatnot. And when you actually see them opening, it's like when you see a submarine opening like its missile tubes for the first time. It just looks so odd. And then you realize like how massive submarines actually are to fit like all the stuff that they have inside of them. But yeah, it's just so
To do
cool.
that, we need to minimize the strength of the return signal. There are several mechanisms for a radar wave to be reflected. The most significant and most obvious way is through spectral return, otherwise known as regular reflection, like a mirror, where the angle of reflection equals the angle of incidence. We want to avoid large, flat surfaces that could reflect straight back to the radar receiver. Corner reflectors, where two surfaces are set at a 90-degree angle to each other, need to be avoided at all costs. Tailplanes consisting of the vertical and horizontal stabilizer are the perfect surfaces to create a corner reflector, allowing radar to bounce off both surfaces and return right back in the direction it came. The best way to avoid this is to remove the tail completely, like the B2, but this impacts maneuverability greatly.
It seems so simple,
Instead,
but
we can replace
definitely
both
not.
the horizontal and vertical stabilizer with a V-tail, as seen on the F117 Nighthawk. The V-tail can act as both a rudder and an elevator, and we
It
can
doesn't even look like they changed the angle that much, but I mean, I guess just doing a small thing like that, like a small change like that, just makes it so much more stealthy.
see how by examining the resultant force generated when the control surfaces are actuated to different positions. We can actuate them in opposite directions to generate a horizontal resultant force, providing yaw control as a vertical rudder would. Or we can deflect them in the same direction to provide pitch control as a horizontal elevator would. This configuration is sometimes used for unique-looking aircraft like the Cirrus SF-50, allowing it to mount a single tiny jet engine on top of the fuselage,
No kidding.
with its exhaust directed straight through the V-tail.
That
A
thing does
private
look
jet
pretty
so
gnarly.
tiny and lightweight that it can deploy a parachute to rescue itself in emergencies. Having rudder and elevator controls linked to a single mechanism like this is not ideal. Fighter jets like
You got to
the
be like
F-35
super fancy to just have like that as your private jet. I don't know like what the other benefits are. I mean, if it has an engine like that, it's probably pretty fast. And I guess, you know, it is small so they can do that parachute thing. But other than that, I don't know why else you'd want that specifically.
and the F-22 need superior control authority, and that is a function of control surface area. The larger the elevator, the larger the pitch control. If a control surface is working a double role, where rudder and elevator action is needed at the same time, it reduces the control authority. So, both planes also feature large elevators, offset by a distance and angled to prevent corner reflections.
That's so
We can
slick.
see many more trade-offs in design by comparing the F117 and the F-35. in the
I wonder how
quest to
many
fulfill both
F117s were
stealth
made.
and fighter requirements. Both the F117 and B2 have their engine air intakes mounted on the upper surface of the plane, which prevents ground-based radar from bouncing around inside the intake and back to the receiver, and helps reduce
Again,
infrared heat signatures.
Seems like a
However,
simple
for a plane
change.
expected to make high angle of attack maneuvers in life and death situations, this isn't a design you would want to include. While performing a maneuver like this, the air intake will receive lower pressure air, which will lower performance right when performance is needed most. Air intakes located underneath the aircraft, like the F-16, will cause too much radar return. So, twin intakes located on either side of the fuselage are instead chosen. These air intakes have some clever aerodynamic features too. This seemingly innocuous bump plays an important role. This is aeronautical engineering epitomized. Every seemingly
Leave it to Lockheed
insignificant
Martin,
design
huh?
feature has a purpose. Mounting engine intakes along the body of an aircraft comes with some.
This is why it's awesome to watch these engineering YouTube channels because, I mean, you see stuff and it looks kind of mundane or it's kind of just there for aesthetics. But again, they can sort of break down every little thing that we're not really picking up on and explain like the actual purpose behind it.
Issues that pylon-mounted engines avoid. As air travels along the length of the body, air begins to form a layer of slow-moving, turbulent air called a boundary layer. If this air is allowed to enter the engine, it not only lowers performance, but it can also damage the engine. As the turbine rotates, it will
too
pass
strong or
through the
something?
slow boundary air
Oh,
on one
no, it's
side
not.
and then
It's
fast
slower.
stream free air on the other. This means the force on the turbine
Or, like,
blade
bend it or
changes
something?
for each and every rotation, causing cyclical bending, a recipe for fatigue failure. Planes like the
Interesting.
F-16 feature a boundary layer diverter that separates the inlet from the fuselage with a small gap. But this design increases radar cross-section and increases drag. Later variants of the F-16 tested the DSI, the divertless supersonic inlet, essentially a large bump that creates a region of compression that pushes the boundary layer air away from the inlet, while also scattering incoming radar and lowering drag. The test flight demonstrated that it could meet performance requirements, ushering in its introduction to the F-35. The final product reduces weight by 30% and lowers production and maintenance costs.
Jeez,
Moving
like a
down the
triple
plane,
whammy.
you can see other hints of stealth design. Long, sharp edges are the enemy of stealth. Sharp edges causes radar waves to scatter in
The
all
F-35
directions.
seems like pretty
Radar
sharp
can
though.
even travel along the length of a surface in the form of a traveling wave and then scatter upon reaching the trailing edge. The strength of that return signal can be reduced with a few clever techniques. The strength of the signal will depend on the length of the edge. So, the first technique is to reduce the edge length with serration. You can see this technique implemented very clearly on the trailing edge of the B-2. However, it's less obvious where it's used for the F-35.
Yeah, I saw it up
until
front a little
you start
bit.
looking at all the access hatches hidden around the aircraft. Every single unavoidable surface gap on the aircraft has a serrated edge.
And again, for a dumb infantry guy like me, like you would just expect it to just be for aesthetic purposes, because like the rest of it has like really sharp sort of edges and it looks like meaner. But yeah, of course, that's not the case. When you're talking about like really expensive stuff like this, especially with like Lockheed Martin, like they're going to put a lot of effort and attention into stuff that actually matters.
This hatch opens to reveal a telescoping ladder to allow pilots to climb in and out of the aircraft.
What the heck?
These open
I didn't
to
even think
reveal
about
landing
that.
gear. These are the internal weapons bay, essential for keeping the radar reflecting missiles hidden from view.
The animation.
And these smaller hatches are flare dispenser doors. Flares are effective decoys for heat-seeking missiles, but they do nothing to prevent radar-guided missiles. In the face of radar-guided missile proliferation and continued growing sophistication in the technology, a new decoy system was developed. This new technology is released from this panel. When needed, this access door opens and a transmitter begins to reel out to a safe distance behind the plane. It has 3 levels of countermeasures to
What the
protect the
heck?
F-35 from attack. First, it actively jams missiles while they attempt to lock onto their target by emitting jamming signals which the onboard computer computes and delivers
snap.
to the emitter through the fiber optic tow line. If the radar manages to obtain a lock,
Fiber
then
optic.
begins
Dang. I know fiber optic cables are like really fast for like transmitting data and whatnot, but I also thought they were like super easy to break. So, I mean, I guess the materials advancement, again, is like a huge focus that the military is focusing on. So, yeah, I guess they're probably increasing the quality or the materials that they're made out of.
disrupting the tracking algorithms, guiding the missile towards its target. Finally, if all is lost and the missile is bearing down on the aircraft, the emitter begins to simulate the aircraft's radar signature, drawing the missile toward it as a decoy. These serrated hatches hide critical
guess it's at a
components
safe
of the
distance.
F-35, but more can be done to reduce edge scattering in these locations. You may notice that the color around these edges is different to the rest of the plane. This is because the edges are treated with a special radar scattering tape. In the same way traveling waves scatter
most
when they meet
expensive
an
tape
edge
ever,
discontinuity,
probably.
they will scatter when traveling over a change in conductivity. The F-35 uses this to its advantage to scatter waves over a longer distance, reducing the return signal by spreading it out. The tape has a conductivity gradient, gradually decreasing its electrical conductivity, causing radar waves to scatter at each interval, slowly decreasing the intensity of the surface wave before it reaches the edge where it would have
conductivity
released one
in
large
tape.
return if the tape was not present. The surface of the
The
plane
tape probably
itself
has, like,
is also
5
composed
patents
of
on
a
it.
specialized radar-absorbing material. In 2010, Lockheed Martin filed this patent for a carbon nanotube infused composite material that can absorb radar waves from 0.1 MHz through to 60 GHz. This is an incredibly wide range of frequencies, notably covering the frequencies Russian surface-to-air missiles like the advanced S-400 system uses. The effect traveling surface waves have on stealth design can be seen elsewhere. You would imagine a cylinder would be a great way to scatter radar in all directions, lowering the strength of the return signal. But if a radar wave comes in tangentially to a cylinder, and the wavelength is at least 1/10 the cylinder's circumference, the wave can actually travel around the outside of the cylinder and travel straight back to the receiver. This is likely why the F35 features a sharp edge breaking up the circular nose cone. Where the F-16 has a nearly perfect circular nose cone, the F-35 features a ridge. The largest hatch on the plane is strangely not serrated, and this is for good reason. This hatch hides the powerful lift fan within. The airflow in and out of this lift fan needs careful consideration. The lift fan is essentially a tiny helicopter, capable of generating 85 kilonewtons of vertical thrust, and in doing so creates a low pressure zone above the plane, violently sucking air into the aircraft at a 90-degree angle. This air has to travel over the hood to reach the inlet, and thus the hood needs to allow air to smoothly pass over it without creating too much turbulent flow.
Okay, I'm thinking like if it just has like really jagged edges, like for some reason the air might catch it a little bit harder and just like start breaking some of the components. But they're even making like the flap aerodynamic, so when the inflow of air is coming in, like they can control that and make it smoother too. Just imagine the countless hours they spent like doing all of this research, enough to like actually understand it and whatnot. And then like, of course, the animations are like probably some of the best I've seen in any YouTube channel. Yeah, this is like some pretty high quality stuff.
The lift fan. This is why the inlet door is not serrated, as the sharp edges would cause distortions in the flow. This hood alone went through several design iterations to optimize the airflow flowing over it. The demonstration X-35 aircraft had two doors opening towards the side of the aircraft, but this was changed for the final aircraft in favor of a rear hinged door. This helps funnel air into the engine and improves pressure recovery on short takeoffs where the F-35B does not take off vertically, instead using the lift fan and directional thrust of the rear nozzle to take off on extremely short runways. The way this aircraft transforms to perform vertical landing and short takeoffs is astounding. It's the closest thing to a transformer we have ever created.
Yeah, for real.
When the time comes,
looks like an insect or something.
Extended drive shaft of the F-35's engine begins to transfer 29,000 horsepower to the bevel gear of the lift fan, spinning the contra-rotating lift fan blades. Simultaneously, gears begin to rotate in the rear exhaust nozzle. The mechanics of this nozzle are another wonder to behold. Called the three-bearing swivel nozzle, it is composed of three airtight segments cut at angles relative to one another. We can change the shape of the nozzle by rotating these angled pieces separately. These three pieces rotate together to smoothly transition thrust downwards.
So I wonder how much the pilot actually controls. So they're saying that you can control them separately, but like what do the controls look like to the point where the pilot can actually like really go to those fine details? I mean, I guess it might kind of like auto calculate if they're just trying to do like a certain maneuver, it'll just like automatically move them a certain way. But yeah, I guess they try and make it as easy as possible for the pilots.
But it's easier to understand how it works by seeing what happens when we rotate segments individually. Rotating the central piece can take the nozzle from 0 degrees down to 45 degrees. This position is used for short takeoffs, splitting the engine's power between thrust and lift. This mode is as impressive as the vertical takeoffs, allowing the plane to operate from shorter amphibious assault ships like the USS Mackinac Island, a ship just 258 meters long. Its minimum takeoff distance decreases even further with the aid of ski jump, a ramp that has been added to smaller amphibious assault ships. Watching the F-35 take off over such short distances is incredible. In this clip, we can see the rear nozzle quickly adjusting its angle of thrust in sync with the rear elevators to adjust the pitch of the plane to ensure a safe takeoff. For a vertical landing,
really is like a spaceship.
The final nozzle segment can rotate to provide the full 90-degree turn. The first nozzle segment can rotate to move the nozzle from side to side, but here it's needed to ensure that thrust doesn't move sideways as the nozzle transitions. As we saw, when we rotate the segments individually, they move in an arc that would cause the F-35 to spin out of control. This mechanism also allows the F-35 to smoothly transition from cruise to vertical flight and from vertical flight to cruise when needed.
Just like, you really need like a team of like hundreds of people for every little component that you're seeing. I say little, but like every kind of like major component that we're seeing here. And I understand if you have Lockheed Martin money, it's like not as difficult to at least afford that. But again, having like some really solid management is key to be able to have all these teams kind of working together. And of course, in the design and the engineering aspect, to make sure that they actually work together and fit together and everything.
There are additional control mechanisms to ensure this precarious balancing act does not go wrong. Bleed air from the main engine bypass is siphoned to 2 roll nozzles located on each wing, providing thrust far away from the plane's center of pressure to control roll. There are also guide vanes located underneath the lift fan. These can adjust the outlet area to adjust the performance of the lift fan, but can also control the thrust of the lift fan from 5 degrees forward to 42 degrees backwards. With computer-assisted control of these control mechanisms, the F-35 is remarkably stable compared to its predecessor, the AV-8B Harrier, allowing the single engine of the F-35 to hover on 2 columns of air. To do this, the F-35's engine, the F-135, developed from the F-119 engine of the F-22 Raptor, had to be incredibly powerful.
The F-22 Raptor is also super
is a
cool.
twin-engined fighter, giving it plenty of excess power to pull off incredible maneuvers. The F-35...
And I know every aircraft kind of has like some nuances that make it better at certain things. Like, I'm not sure if the F-35 would be as good for dogfighting as maybe something like an F-18. Honestly, I couldn't tell you, but like, again, it is really fascinating to break down the engineering aspects of everything so you can understand why certain things are better at other things. Like this thing is just obviously amazing at stealth because they really considered and thought about everything.
It has one engine and needs to squeeze out all the power it can get to perform a vertical landing. Where the F-22's engine can generate 156 kilonewtons of thrust, the F-35's can generate 191. The F-35's engine has a much larger fan and bypass ducting, giving it twice the bypass ratio of its F-22 counterpart, providing the F-35 with a more efficient engine for cruise, but also a higher mass flow rate for higher thrust. Okay. However, this does come with some drawbacks. Air that travels around the engine core completely avoids the combustion chamber, and thus misses out on the acceleration generated there, like reducing the exhaust velocity. This reduces the top speed of the plane. The max speed of the F-35 is 1.6 Mach, and while it's the first plane capable of vertical flight and supersonic flight, the F-22 can fly at 2.2 Mach. The F-35 was optimized for loiter time, not speed. However, all that extra weight needed for vertical takeoff seriously hampers that ideology. The lift fan module weighs 1.2 tons, weight that does nothing in normal flight and requires more fuel to carry. And to make matters worse, that space is used for internal fuel tanks for its variants. Making the lift fan as light as possible was pertinent to making the F-35B viable in the battlefield.
Yeah, I think another important thing to note is like the branches are requesting these. It's not just like Lockheed Martin saying like here's like this different variant. The branches are requesting these. Like, we see this awesome platform, but we're not necessarily going to sign a contract unless we have these sort of capabilities, like, you know, taking off on a short ramp or having the vertical lift capabilities as well. So I think the people who are actually like the end users are kind of, you know, okay with those drawbacks, kind of like a give and take.
The fact it only weighs 1.2 tons is astounding. It contains 2 counter-rotating titanium blisks. Blisk meaning the blades and disc are all one single piece, instead of the traditional alternative of creating a disc and attaching blades through dovetail connections. This improves efficiency and eliminates a potential site of failure in the connection. This is an astounding feat of manufacturing, and the first stage fan takes it even further. The first stage blades are hollow to save weight. Where the F-35B truly comes into its own, however, is in its modern suite of sensors and computers, all feeding into this. The heads-up display incorporated
let's talk about
into
the price
pilot's
point.
helmet. Traditional heads-up displays, like those of the F-16, are incorporated into a panel in the cockpit, a panel which the pilot can't see while scanning their environment. Situational awareness is everything in the heat of combat, and this helmet does everything it can to keep the pilot informed, even giving them X-ray vision and night vision. Information from a suite of sensors around the plane feed into a central computer, where it is processed and displayed through a projector inside the helmet. Inside this transparent faceted box underneath the aircraft is a suite of sensors, but those are not your typical windows. These windows are made from a notoriously expensive gemstone, sapphire.
Oh my god.
One of the few materials that is both hard and durable, but also
I'm just thinking of all the maintenance as well. Like all the gears need like probably very specific lubricant, because if you have like gears with the wrong lubricant, from what I've seen, they can shear themselves like super quickly, and you know, then you kind of lose power to certain things. So that's obviously one thing to consider. But like, I don't know how you would clean the sapphire sensors, probably with like a really sort of expensive cleaner and like a very particular way of doing it. So I don't know, you probably need a massive team of maintainers for this specific aircraft. Even going as far to make sure like none of the tape is kind of like getting lifted up, or like there's no scratches or anything on any of the coatings. Like I'm sure the actual inspection list is like freaking 100 pages.
So transparent to a broad range of electromagnetic wavelengths, from ultraviolet to infrared. However, the radar antenna hidden inside the nose of the F-35 is the most important part of this electronic system.
Oh yeah.
This is a scanned array radar that works very differently to traditional mechanical radar. Phased array antennas have hundreds of tiny antennas. We can see metal plates set in rows in the F-35 phase array antenna. The metal plates have slots cut into them, and each and every one of these slots is an antenna, 1,600 in total. This allows the phase array antenna to steer its radar using constructive and destructive interference. If two antennae release two radar waves at the exact same time with their peaks and troughs lined up, it will result in constructive interference, increasing the amplitude of the radio wave. However, if the radio waves are set 180 degrees out of phase, matching the peaks to troughs, it will result in complete destructive interference, cancelling out the wave completely. This is how noise-cancelling earphones work. They listen to the background noise and then release a cancelling sound wave to create silence.
So I wonder how they like... So it didn't look like they could actually steer the antennas in like the traditional sense, but I'm guessing if you just have like different signals or like, you know, electricity going to it can like change how it's actually scanning. I don't know. That is, again, just insane engineering of the F-35, really.
Use this phenomenon to steer the radio waves, preventing the radar from becoming a giant beacon, leading enemies straight to it. Traditional phase array antennas are passive, meaning every antenna in the array is driven by a single transmitter and receiver. This would mean it can only point in one direction, and if it encountered two enemy planes flying side by side and they split up, the passive phased array antenna would no longer be able to track both of them. However, the F-35's phase array antenna is an active phased array, meaning
that's be
each
pretty
and every
helpful
one of these
for
antennae is an
situational
individually
awareness.
driven transmitter and receiver, meaning the F-35 can track multiple targets at once with zero moving parts. The nose cones hiding these antennae need to be transparent to radar waves, and are usually made from glass fiber composites as a result. This transparency causes issues for the plane's radar return signature, as an antenna like this will reflect signals. This was a much bigger issue for mechanical radar dishes that needed to point at the enemy to keep track of them. The phased array can point towards multiple targets while staying in a single position, and this is why it is pointed skywards, to bounce incoming radar to space. The phased array antenna also acts as the plane's communication antenna, and this is critical to the F-35's battle doctrine. The F-35 excels in battle because of its networking abilities, relaying information between its squadron. This is a huge amount of data to transfer between aircraft and allies on the surface, and requires a high data transfer speed. However, communication comes with one glaring problem. It announces your presence to anyone listening. It is vital that stealth planes can communicate with each other securely, and the active phase array antenna facilitates this. The F-35 uses the latest data link system, MADL, improving on the experiences learned with the F-22, allowing the F-35 to quickly share data securely from individual F-35s and ground-based systems. This information is then sorted by the computer and presented to the pilot in their heads-up display right in front of their eyes.
Now you can be a subject matter expert in like any domain that you're working in, but I would never consider like half the stuff they're talking about, all the signal stuff, all the aerodynamics, the armament, the material science. And for them to put it in a video that's like not too long, I know I'm making it kind of long, but the video itself is not very long, and you know, they're able to regurgitate it so it's kind of like digestible for us. is like, again, even more impressive.
giving them unparalleled situational awareness. There is no need to communicate with their wingmates if there is an adversary underneath them. The planes communicate and feed that data right into the helmet, allowing the pilot to look underneath the plane and see the location of the adversary themselves. This is the true strength of the F-35B. It is a networked hive mind stealth fighter, capable of taking off from a ship a fraction of the size of an aircraft carrier and returning while hovering in the sky like a helicopter. It's one of the most remarkable pieces of military technology ever created. The F-35 has borrowed many lessons learned from planes like the F-117 Nighthawk and B-2, planes that we have not made documentaries
low
about
polygon
yet,
aircraft.
but our friends over at Mustard have. Their B-2 documentary
Nice.
is 20 minutes of beautifully crafted story filled with stylish 3D renders. If you liked this video,
I do
you'll
actually kind of want to
definitely
check that
love
out,
these
because
originals.
the
You
B2
can get
is
access
just
to
such
them
a
by signing up with the Real
interesting
Engineering link
aircraft.
in the
And
description.
I don't even know what kind of
You can
operational
sign up
experience it
directly
has,
to
to be
Nebula
honest.
for
Okay, I know I can talk a little bit too much sometimes during these videos, but yeah, there was just so much we had to like slow it down and kind of try and process. So yeah, I apologize if the video is a little bit longer, but you have to admit a lot of that stuff, like all of it was just super, super interesting. If you have like any sort of like a love of learning, really, like I do, I think everything is fascinating. Even if I'm not like an expert at anything like signals intelligence or electronic warfare or anything like that, it's still cool to be able to like generally appreciate the work that went into it. Of course, you're never really going to understand like how many countless hours, days, years, and the amount of people that went into developing all these like, you know, components. But again, it is nice for this video to kind of regurgitate it so we can generally appreciate it. And again, the title is pretty fitting, The Insane Engineering of the F-35. And yeah, the F-35B, again, is going to be a little bit more tricky, I guess, just because it's got like all the, you know, vertical lift capabilities. But yeah, hopefully you guys enjoyed. Hopefully you guys learned something at least. If you didn't learn something, you're probably lying, or you're just like working directly for Lockheed Martin in like a super high position or something. But yeah, that was really cool. And again, I'm sure we know a lot of work went into the F-35. They have Lockheed Martin money, but the work that went into this video is pretty freaking astounding as well. So definitely go and give them some supports. But yeah, of course, if you guys liked this video, hit the thumbs up, comment, let me know what you think. If you have any other cool information about the F-35, let us know down below. Because again, he went over a lot of like the small stuff, like the gradient for the tape. This, I don't even know, the conductivity gradient of the tape. That's probably the thing that's sticking out in my mind the most. But if you guys know anything else that's like kind of cool or interesting, definitely put it down in the comment section so we can go and read and learn a little bit more. Hopefully, you know, I'll have some time to regurgitate what we just learned before I read anything else. But yeah, that's it for this video. I'll see you all in the next one.